Warning: the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to moving into limits. This is your first exposure to limits in a calculus setting, or hopefully it is. And we're going to go through kind of slowly with the basic concepts of what a limit is. Trust me, you want to start low level with the basic concepts and work your way to the advanced concepts with limits, because if you just dive into the deep waters, it'll be overwhelming. All right, the basic concepts of limits. We have four kinds of limits we're going to actually deal with in calculus. They are FF, FI, IF, and II. I know it seems kind of weird, and I don't know of anybody else who writes it that way, but I do, because you have to think about this in terms of outputs and inputs. All right, outputs and inputs here. So one type of limit is when our outputs are finite and our inputs for our function are finite. We call those finite limits at finite points. The next style of limit, which we'll reserve for a different video, is when our outputs for our function are finite, or basically I should say outputs for our limit are finite, but our inputs are infinite. Those are called finite limits at infinities. Then you move to what if our outputs for our limits are infinite, but our inputs are finite? Those would be infinite limits at finite points. And finally, what if both our inputs and outputs are infinite with regards to the limit? That would be infinite limits at infinity. For now, we're only focusing on the finite limits at finite points because that's actually the core initial part of limits. We'll get to the other ones later. Let's start with definition of type FF, finite. So a finite limit at a finite point. And again, I want to stress, this is a non-rigorous definition. We'll have the rigorous definition in a future section or in a future video. The notation, LIM, where you have f of x there and an L there. I'm going to write down how you would read that. This is read as the limit of the value of the function f of x as x tends to a is L. What that really means is as x gets super close to a, within what we would call a delta neighborhood of a, the function values or the y values for the function tend to a value of L. That's really what that notation means. Officially, it's much more detailed than that. So let's go ahead and step into the lower level of the true definition. This is not the true definition, but the lower level version of it. So that notation means that we can take the values of f arbitrarily close to our value of L by taking x sufficiently close to a, but not equal to a. And this goes back to the previous video that I did on neighborhoods and punctured open neighborhoods. For this function right here, you can see that as x gets really close to, let's just say, this value, we'll call this value a, as our x values get really close to that value of a, the y values for the function get really close to this y value of L. Let me just mark it out here. So again, as x gets super duper close to a, and we're just going to say within some neighborhood of a, so these x values get really close to a, but not including a. We're not really concerned about at a itself. But as x gets really close to a, notice the corresponding y values get closer and closer to the value of the function at a itself. Again, from either side, the y values just get really close to this value right here at the height of L. And that's where we start to bring together the conversation from the previous video about punctured open neighborhoods. We have this delta neighborhood about x equals a. All x values in that delta neighborhood lead to y values that are in what we would call an epsilon neighborhood of L. So a wiggle about L. Of course, I'm not actually doing an appropriate one here because I'm not doing the true definition yet, but that's the basic idea. So as x gets close to a, the y values get close to L. That's what that definition means, or that notation means. Now, because the true definition of a limit can be very, very bulky and hard to understand, I take my time developing it. And right now, we're just going to do things numerically. You can actually, there are actually several ways you can evaluate a limit, and they are progressively better and better and better. The worst way you can evaluate a limit, honestly, is by building a table of values. Let me write that down. Building a table is, in general, the worst way to evaluate a limit. However, we're going to go ahead and do that now just because it's the introduction to limits and it's a good idea just to see how they work. So let's hop over to Desmos to build a table of values for this function right here, and we'll investigate what happens to that function as x gets really close to 0.
Now, there are two ways to actually build a table of values in Desmos. One would be to use the math tools, the scientific calculator. That's not the best way to do it, but you can do it. If you want to do it this way, you just type in your function, f of x is equal to, and our function was e to the 1.2x minus e to the 2.3x over x. So you could do that, and then it really isn't truly building a table of values more than it is just testing this function at a lot of values. So you say, what is f of? Remember, we want to know what is the value of this function as x approaches or gets really close to 0. So we'll test values near to 0, like 0.5 or f of let's say 0.1 and so on and so forth. So you could do it this way. You don't want to plug in 0 because you could see that would cause division by 0 in your function. And don't forget, you need to test both sides of 0. So you want to try the negative values as well. You don't want to just try the positive values because there could be some weird behavior on the other side of 0 that you wouldn't be catching. But in this case, you could see that when we build this list, it's not really a table, it's more a list, but when you build this list of values, it ends up working very nicely to give you an approximate value for that fraction as x approaches 0. It's roughly negative 1.1. Now, you do need to know that it would likely be in a homework that you're asked to approximate this limit as x approaches 0 to, let's say, 3 decimal places. And in that case, doing this probably not the best. So the other way you can do this is to go to Math Tools and go to the graphing calculator. I already have that set up over here. When you do that, let me open this up slightly. When you do that and you type in your function, you'll actually get a graph of the function, and that's a little distracting. So I'm going to turn that graph off, and I'm going to zoom in as well. I'm going to add a table. My inputs will be x sub 1, that's fine, but my outputs will be f at x sub 1. So let me type that in, f at x sub 1. Subscripts are done using the underscore, which is shift minus sign on your keyboard. And then you can go through here and type in values. I got all the positive values in, and you can see that as x is approaching 0 from the positive or the right side of 0, the values definitely are approaching negative 1.1. Now let's try the left-hand side of 0, and I'll just do this actually this way. I'll just put minuses in front of these. And you can see that, again, it is going to approach negative 1.1 when rounded. So therefore, if you were asked to round to 3 decimal places, it would just be negative 1.100.
Now, I'm not sure what happened on my printout of my PDF here, but it was supposed to be example 2.2 number 2, so I just wrote it in there by hand. Anyway, let's go ahead and hop back to Desmos because this is one of my favorite examples to do for a class if we were on ground. It is a really neat example, but let's go ahead and hop over to Desmos right now and look at the limit as x goes to 0 of sine of pi over x.
So now we're back here at Desmos, and I want to mention something before diving too deeply into this example. Calculus only works in radians. So make sure that whatever calculator that you're using automatically works in radians. Luckily with Desmos, when you're in the graphing calculator screen, you're automatically working in radians. You can see that off to the right by clicking the wrench icon, and the radians is highlighted. It's automatic there. Whereas in the scientific calculator, Desmos has a default to degree mode. So be very aware of that in the scientific calculator, it's in degree mode, but in the graphing calculator, it's automatically in radian mode. Now I want to evaluate this function as x gets really close to 0. Notice I'm calling it f of x, whereas in the problem we were dealing with, it was just the limit as x goes to 0 of sine of pi over x. I just want to use f of x here so I can build a table. So I'll add a table here, and I'll change the outputs to be f of x sub 1. And now I want to allow x to get really close to 0. And this problem I absolutely love because it showcases something wrong with using tables. So let's suppose that you plug in 0.1 and 0.01 and 0.001 and so on and so forth. Now, if you were to believe this, it looks as though this sine of pi over x function is approaching 0 as x is approaching 0. And in fact, you could test it on the other side as well. I could put negatives in front of these, and you would get down to the same exact results. So that's kind of nice, but there's something that you're being lied to about here, and we'll be able to see it if we try some other values, because we only chose 1/10, 1/100th, 1/1000th, 1/10,000th, and 1/100,000th. By the way, just to let you know, this number right here is essentially 0. It's just a rounding error by Desmos that causes it to say that it's something times 10 to the negative 12th. Well, if we try maybe a 0.2 and a 0.02 and a 0.002, we get pretty much the same or exactly the same results. So again, very convincing that this function, sine of pi over x, is approaching 0. Let's try this with a 0.3. Now this is interesting because if I replaced all those end digits, the ones, then we replace those with 2, and now we're at 3, all of a sudden replacing with 3 creates something completely different. This is negative 0.8660254. By the way, that's negative square root of 3 over 2. So this is contradicting all of our previous results. And if you tried something like 0.4, we get even more interesting behavior. The outputs start at 1 and then turn into 0 right after that. We can try this with 5, and you can see that it all turns into 0. Now we'll try 6. 6 is really interesting because it starts at a negative square root of 3 over 2 and then switches to square root of 3 over 2 as x tends to 0. Let's try 7. Building a table of values, we are getting all these different possibilities just depending upon what our final digit is. I recommend that you go ahead and try this on your own with a few other values. Try 8 and 9. There's only 2 other values you could try there, but you'll see that they're not the same as the previous values of 1 or 2 or 3. So this begs the question, why do we even bother using tables if we suffer from this inaccuracy? And why is this happening? Well, before answering those questions, I want to take a look at the graph of this function. So I'm going to go zoom out a little bit, and here's the function right here. This is the sine of pi over x. And as x gets really close to 0, you can see that our values for our functions just start wiggling back and forth infinitely many times. And that is the issue, is that as we're getting really close, as our x values are getting really close to 0, the function values just hop between a bunch of numbers infinitely many times. And that is because we're about to have division by 0 at x equals 0. In fact, what we're going to mention in a future video, in a couple videos from now, is that when you have a finite number, like pi, over a very small number, like something near to 0, the fraction that you're looking at is actually pretty large. pi over 1/1000th is actually 1000 pi. And so that causes the sign to act as if it's moving faster and faster as its denominator is tending to 0. And you can see that in this graph right here. And I went ahead and zoomed in to where we're looking at negative 0.1 to positive 0.1. And you can see as I move my x values to the right here, that as I move, even if I'm moving my cursor at the same speed, the values get faster and faster and faster and faster as it gets closer to 0, as x gets closer to 0. And so this is the issue. It becomes infinitely dense, if you will. And I could zoom in, and it is an infinitely dense picture of this graph. But that still doesn't answer the question, why are some of the choices for the last digit that we're testing, why do some of them always return 0? I mean, I think that's a very basic question, right? Why is it that when we plugged in all these values with a 1 as their final digit, why did it return 0? Well, think about this. If x were 1/10, then pi over x would be pi over 1/10 or 10 pi. Sine of 10 pi is 0. If x were 1/100th, we'd be looking at sine of pi over 1/100th, which is sine of 100 pi. And again, that would be 0. This argument goes on forever. If you were looking at x equals 1/1,000,000th, for an example, you'd have sine of pi over 1/1,000,000th, which is sine of 1,000,000 pi, which again is 0. So when your final digit is a 1, that's why it constantly returns 0. However, when your final digit is a 7, all bets are off. Because now, for example, in the first case, sine of pi over 7/10, that's sine of 10 pi over 7. That does not turn into 0. So our choice of 1 as the final digit caused this sign to act very nicely, but the choice of 7 as a final digit, that does not allow sign to act nicely. By the way, you could also test this with a 2 as the final digit, and you'll find out that these will all become 0. And the reason why is very much the same reason as to why when the final digit was a 1, the sign turned into 0. Because again, sine of pi over 2/10 is the same thing as sine of 10 pi over 2 or 5 pi, which is 0. You can test this out all day long. This is a very interesting example, and the result is because all of those limits were not infinite, but simultaneously were not finite, right? Because they're bouncing all over this place. We do not know, no matter how we built our table, we do not know what the value of that sine of pi over x is as x approaches 0. It doesn't become a single finite number, because if I plugged in different values, let's say the 7 here, you get that the sine of pi over x is bouncing all over the place. So yes, it doesn't go to infinity, but also it doesn't become finite. And because of that, we say this limit does not exist. There you have it. Although obviously you would handwrite that on your homework, quiz, or exam.
Now let's go ahead and again, we're going to hop back to Desmos. This time we're going to just look at things graphically. So the previous two examples were all about building tables of values and using a table, which again is what I said earlier, it's the worst way to evaluate a limit. And now what we're going to do is look at a graph and investigate limits using a graph. That is the next best way, honestly, to evaluate a limit. The worst way is using a table, and then one step up from there, not too far from that bottom level, is using graphs. Both of those you're going to let go of in the long run, but for right now, we're going to go ahead and use a graph to investigate some limits.
Now, this style of example, this is kind of important. In fact, it's very important. So we are going to use the same graph for many different examples, but for right now, let's go ahead and just focus on finite limits at finite points where the limit exists, and maybe one where it doesn't. So let's take a look at, let's suppose that we want to know what happens to this function, whatever this function is, as x approaches -1. Now, graphically, if somebody just hands me this graph, this is actually not bad. So I'm going to go ahead and zoom in here. You can see x equals -1 right there. And if I click on it, you'll see that the value at x equals -1 is 0. However, that's not what we're asking. We're asking actually, what is the limit of the function as x approaches -1? Well, that just means as x values get close to -1, what do their y values approach? And you can easily see that it is actually going to be 0. But remember, the definition of a limit tells us that we're not concerned about the function's value at -1 in this case. We're just concerned about what the y values become as x gets close to, but not equal to, -1. And as you can see on either side of -1, that the limit does approach 0. Those y values are approaching 0. Now, why am I making a big stink about not worrying about the value of the function at -1? Because if I change the question to what's the limit as x is approaching 2? Well, as x values get close to 2, you can see the y values, they're right now at 7.793, and then they become something closer to maybe 0.85 and so on and so forth. In fact, the closer I get, let's see if I can get really close here. Let me zoom in. The closer I get to x equals 2, you could see that it's getting close to maybe 0.84, a little bit above 0.84 in fact. Okay, so I'll say a 0.841. That's what the y values are approaching, at least from the left-hand side. Let's see from the right-hand side. So from the right-hand side, you see the same issue, right? That we're getting really close to 2. And again, 0.841 if I had enough fine detailed in there. Maybe a 0.842 even, but we'll just call it a 0.84 just to make life easy for us. So I think we could all agree the y values seem to be approaching a height of 0.84 on both sides. However, the value of the function at 2 is actually 2. So this is a good example of not really being concerned about the value of the function itself at x equals 2. The limit as x approaches 2 is 0.84. Nobody cares about the value of the function at 2. And in fact, that point need not even be there. We could say that the function doesn't even exist at 2. That's fine. Still, the limit as x approaches 2 for our function is still going to be 0.84. So this is a critical concept within calculus, is that when you're taking a limit, you're not concerned with the value of the function at the point. You're just concerned with the value of the function near the point. All right, let's take a look at a different style of example. So I've zoomed in to that little wiggly area on the graph. Let me zoom out to show you what I'm looking at. I'm looking at this area right here. And this is indicative of where a limit will not exist. And so it is true that the limit as x approaches, let's say 1.3183, that limit will exist. It'll be 0. From the left and the right sides of 1.3183, the y values are approaching a height of 0, both from the left and from the right. But there is some value in here, let's say at 1. Okay. At x equals 1, while the value of the function is 0, as you approach x equals 1 from the right-hand side, the function just bounces back and forth infinitely many times. Let's see if I can actually showcase that. So you can see the y values are all over the place from the right-hand side. So this tells us that coming from the right, we can't guarantee what the y values are going to be. Maybe coming from the left, we can. As we come from the left here, it looks as though the y values are approaching, I don't know, about a 0, I would say. But then all of a sudden, once you get beyond 1, it just jumps around forever and ever. So this is a topic that we're reserving for the next video, which is called a single-sided limit. In this case, from the left-hand side, I could tell you this function is approaching a height of 0 as x approaches 1. But from the right-hand side, this function is all over the place as x approaches 1. So this is a critical topic within limits. But for right now, all I really want you to focus on with this video is that we can determine for a nice smooth continuous function like this the value of the limit as x approaches anything we want. For example, x equals -1. It's very easy to see the y values on both sides are approaching 0. Same thing if I want to know what's the limit as x approaches 0. Well, from the left-hand side, the heights are going to approach -1. And from the right-hand side, the heights are going to approach -1. And finally, very important example here, as x approaches 2, right? The heights are approaching 0.84, I think is what we agreed upon. And from the that's from the left-hand side. From the right-hand side, it's 0.84 as well. So the limit there would be a 0.84.
Finally, to wrap this up, I just like to round out each of my lecture videos when it comes to limits with a roundup of what we've covered, because this topic is so massive. It actually covers an entire chapter, entire unit of material in calculus. So important to constantly go back to the beginning and say, here's where we started, here's where we're going. So right now, talking about inputs and outputs, so inputs being our x values and outputs being our y values, we have investigated the limit, which is the finite limit at the finite point. In other words, x is approaching something finite, that's the finite point, and the limit, L, is finite as well. So we have a finite point with a finite limit. That's the case we have investigated so far. And remember, that just means that the values of our function can be made arbitrarily close to L by taking x sufficiently close to A. Or, in other words, that notation means the values of f will be in a small neighborhood about L for x values in a sufficiently small neighborhood about A. All right, in the next video, we'll go ahead and increase our level of understanding of limits by talking about single-sided limits.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.